So first off, to define pressure, I would define it as the force exerted on a surface. When you go to the doctor, they will take a blood pressure. That's the liquid pushing on you. Maybe throw away your Dixie cups. Let me keep those. Air pressure is the air pushing on stuff, which is what I refer to with the second part. What creates air pressure? That's just the gas molecules moving around and colliding with stuff. So we want you to be able to think about something that you can't see and yet explain it. It's a pretty common thing in this class as we move forward because we deal with chemistry that occurs at the atomic level. Yet we cannot see the atomic level. We can only see the result of that. You saw the result of a lot of this today, of the push in, the pull out, the cup into the water, the marshmallow gets smaller or bigger. We should be able to explain what's happening then in those different scenarios. So again, pressure is just that force exerted when things are bouncing around. We specifically will be talking about air pressure in this class. So again, air pressure is the pressure on you and everything else. It's measured with what's called the barometer. If you've ever watched the weather report in the morning, you'll hear them talking about things like it's 29.2 inches of mercury and rising, or here comes a low pressure front from the southwest coming in. We can measure that pressure of air. Now, what I've shown on the bottom left, right-hand corner of the note sheet here is one of the first barometers that we had. They would take a tube and fill it with mercury and put it in a bath filled with mercury. Air would be pushing down on this, and the more air pushed down here, it would cause the mercury to come higher up the tube. If a low pressure front was coming through, that means there's less push here, which means it can fall down a little bit more. Now, these values I have for sea level aren't ones that you really need to be aware of necessarily. Again, there are a couple different measurements for the unit of pressure. Millimeters of mercury is a very common one. Atmospheres is another common one. I like the last point on this slide, which, by the way, when I say normal pressure, that's what I'm referring to. So if on your note sheet, when it says what is considered normal pressure, it's the sea level pressure. So that you can kind of feel it right now. Higher altitudes. I mentioned this earlier with the airplane example. Higher altitudes have a lower pressure. If you've ever heard the expression, the air is thinner up there, it's because it's true. There's less gas molecules the higher up we go. And if the molecules are of less number, they can't exert as much of a pressure. Athletes will sometimes train in high altitudes because they're breathing in less oxygen because there's less O2 there. And then when they go back down to lower altitudes, now their body knows how to perform with even more of the good stuff to help them out. And that's why you have high altitude training at times. So again, the second slide dealing with how do we measure millimeters as a unit of distance, and we can actually measure pressure in that based upon that example of that barometer on the right-hand side. Nowadays, all our barometers are digital, so we don't just have pools of mercury laying around. But to think about air bouncing around having its effect on things. Maybe you've even heard before that there's different cooking directions when you're up in Denver versus down here. It's all because higher altitude has lower pressure. So that air's exertion of force on us. Another term that's very commonly used when describing pressure is what a vacuum is. And I'm not referring to a Hoover, although the principle of how that cleans up your carpet is dealing with this. A vacuum is defined as a space that is empty of matter. If you don't have any matter present, there can be no pressure. Zero would be the measurement for the pressure if there was nothing there. In actuality, my second bullet point says it's very difficult to have zero pressure. So in other words, what we usually do is refer to a vacuum as significantly less pressure than normal atmospheric pressure. Next class, to remind you of what we've gone over today, I will bring in a vacuum pump. Actually, Mr. Butters, I believe, is using it with his class today. I'll use it next time, and show you how we can alter the pressure of things. I mean, you altered pressure with a syringe. I have a thing that pumps air out to do the same sort of thing. Last thing I have to mention on this slide is outer space is as close as we can get to a perfect vacuum. Again, any section of outer space has limited, very limited amount of gas molecules around, because those gas molecules would naturally be attracted to planets, gravity, and so they'd be there instead of just floating around in space. So in outer space, a lot less pressure. Think about you pulling out the syringe, made the marshmallow expand a little bit. Boy, if we had that marshmallow also put in outer space, it would just go and go and go and go. Again, it'd be like the movie Total Recall, where the guy exploded because pressures try to balance each other out. I am going to go over now with you an example that happened to me dealing with pressure a few years back. So, again, nothing we have to write down, but we are coming upon almost 8 years that this happened to me. Most people remember very recently there was an explosion in Sun Prairie. A gas pipe leak caused a good chunk of that downtown area to explode. 8 years ago, I lived in Sun Prairie, and 2 doors down from me, there was a house that exploded. And if you know anyone who lived anywhere near Sun Prairie, they heard the explosion from like 10, 15 miles away. It was the loudest thing I've ever heard in my life. I can't really explain it because it happened at 3 in the morning. So you just were jolted awake by this explosion. Now the explosion itself, this is a picture from my house. So you're sitting where my house would be. Next to it, you see the screen-in porch of my neighbors. So right here. On the other side used to be a house. So they had a gas leak. I believe there was furnace was leaking, and then a pilot light ignited that gas. And when you have flame and a flammable gas, bad things can happen. What an explosion basically is an uncontrolled release of energy. Matter absorbs energy. Started the class by talking about that with the boiling water and the heat. The matter that's most likely present is the air all around. Those gas molecules gain energy, and when they gain energy, they move faster. And when they move faster, they are moving with force. My neighbor that lived right here, every single drywall part of their ceiling broke. So when they were shaken awake, and then we all had to evacuate our houses, they said it was like snowing in their room because all that insulation above your attic was all coming down on them. Their house shook so much that it just split the drywall. Our house, being 2 doors down, it shook a lot as well. Now this is from my front doorstep. There were shards of glass all over the place. Maybe I'll flip the lights to help you see this a little better. See in the bottom left-hand corner, window frames all over the place. I mean, it was difficult to clean up. At the time, I only had 1 child, but she was young, and we didn't want her crawling around in our yard because there was glass all over the place. We had to hire someone to pick up glass. I tried to keep a clean home. You would not normally see a line of grime where my kitchen sink is. Our house shook so much that it moved the kitchen sink off of the countertop a little bit. We had hanging lights in our dining room. That hanging light swung and hit the ceiling, and the wiring broke free, so then that wasn't working anymore. But the biggest issue that I want to talk about from air pressure, was the side of my house that was closest to the explosion. This is called your soffit. And notice how this is all mangled. Yes, there's a broken window right here as well, but this is all beat up. This was all caused by air. The explosion happened and air rushed in and broke this window. So when it broke through this window, a whole bunch of air was filling into my garage. At some point, all that air built up an area of high pressure. Think about you pushing in on the syringe. When you pushed in on the syringe and that let go, the syringe popped out, right? Same thing happened with my house. That my house popped out. Air rushed in, this entire wall moved out. The only thing that stopped this wall from moving out even further is my gas meter. Which is kind of scary to think about, that the only thing that stopped my house from falling off its foundation and then possibly coming down was the thing that has the gas that, if it leaked, would then be leaking explosive gas that could start my house into an explosion as well. If you look in the inside of my garage, you might see a little white painted line here. When I put on this boards onto my garage, that was the line that was from my paint job. It was a garage, so I didn't care if I got a little bit of paint on that frost wall and that concrete. You can see how far that wall moved. It was air that moved that wall, and only air. Again, pressure built up on the inside. Maybe we go from the side view here. Pressure built up on the inside. Internal pressure was greater than external pressure. A balance had to be reached. In order to do that, the wall kicked out. I had to hire people to try to fix this. You can't live in a house like this because it could come down on you still. Brought in skid steers, things like that. They could not move this wall back in. Air was able to push the wall out. They couldn't push it back in. What they had to do was jack up my roof. Get my roof off of this wall. Then they could push the wall back in. Then they could put the wall back down. Or sorry, the roof back down. So again, to me, this happened 8 years ago, middle of the night, but it's an example of what you just saw today with Boyle's law, which I think is the next thing on your notes. Pressure and volume are inversely related. So in other words, if you put a gas in a small space, it's going to have a high pressure. If you put a gas in a large space, it'll have a low pressure. We should have noticed that with the syringe. I'm just abbreviating that with a increased volume, decreased pressure. Now, some students can memorize this relationship between Boyle's law, pressure, volume. I like the last bullet point because it's trying to explain why. Why does this occur? If you increase the volume that gases are occupied in, they can't bump into each other and other things as often. That bumping into stuff is what pressure is. So by increasing the volume, you decrease the pressure. That's what you saw in the syringe. Now, in my example that I showed you at the house, it was more of adding air, adding air, adding air. If you add more air, there's more pressure. Think about this classroom. If I had another 50 people in here, we'll be bumping into each other all the time. Think about this class here. If I took you and put you in a room half the size, we'd be bumping into each other all the time. But if I took you and put you in the gymnasium, we could spread out. And that analogy, we're the same as gas, of either bumping into each other or more spread out. But that pressure, that stuff that we can't see from the air molecules, we can see the effects of it, however. Now, there are 3 entries still on your notes, because what we're going to cover next class is how temperature can affect the behavior of gases as well. So let's just hang on to that note sheet for next